Because the inner theorem, this thing is equal to this. If I take the mod square of this will also be equal to 1, and the probability will not be affected. Now when I say like this, then this thing and this thing are the same, and I take the mod square, then it means this mod square is equal to 1. So E, I, K, and A mod square is equal to 1, and it means that this thing is equal to 1, and this is possible only because I know that EIX is from Euler formula cos x and I sine kx. So from here I can write that this is possible only when this x is equal, means when this k n a is equal to 2 pi, because cos 2 pi is 1 and sine 2 pi is, this is x only, and sine 2 pi is equal to 0. So this is possible only when k and a is equal to 2 pi, or I can write that the value of k from here will come out to be 2 pi over n a. But I know one thing, that this thing is true for 2 pi as well as 0. For 0, this thing is true as well. And this is true for 1. For example, if I write that this thing is n times this, and n is 0, so this is true, because if I put here 0, then this thing will be equal to 1. If for this I put, for k I put, for n I put 0, then this thing will be equal to 1. The same it is true for n equal to 1, when this will be equal to 2 pi. This is true for n equal to 2 as well, and 3 as well. Similarly, the cos pi will give you this for plus minus, this is true as well, for plus minus and so on. So this is true. When n is equal to 0, we will have this thing again 1. For n equal to plus 1 or minus 1, again we will have this thing equal to 1. So there will be a restriction for k being real. So k is supposed to be real. Then we are able, means k we supposed, and now we found the value of k here, that what will be the value of k being a number and real number. So we found the periodicity here. We resolved the issue with the Bloch theorem of the periodicity, and now we are set to solve the motion of electron in this material with the help of the Bloch's theorem, and we will utilize the beauty of the Bloch's theorem. If we solve the electron behavior or electron motion in this block, then we can apply it to the rest of the material with the help of the Bloch theorem. So I can write that the Dirac Coulomb potential V of x I can write is, this is alpha summation, and j runs from 0 to n minus 1 delta x minus j a, and this will have the nth spike, means the spikes that I am considering the Dirac potentials, delta potentials. This side, the nth will come on the x minus nth spike is 8x minus a. Now let's discuss this one. What will happen? That the spike, where the spike will be, when j is equal to 0, we will have this thing is delta x, and we are at this point. Our potential will be v of x. When j is equal to 1, we will be at this position for delta x minus a, and so on, and when we will move it around, then the nth spike will come at x minus a, and the periodicity will continue. So if we solve the Bloch's theorem for one cell, where one cell is between a and 0, then we can apply it on, means we will have to solve the Schrödinger wave equation for this one cell under this potential, and we will apply it to the rest of the material. Now the one cell here is this one. We are in this block here, and here the potential is a spike. This spike is going to infinity, too high. This is Dirac delta function, and this is another spike. It's going to infinity. So we are in the regime of infinite square well here. That what we solved earlier. So if I solve for this block, I can apply it on the rest of the blocks. And now let's start with, within this block, we are having the from 0 from x in between 0 and a, I can write that for x in between this, v of x is equal to 0, as it's a spike potential, the delta potential, and I can write the Schrödinger wave equation minus h bar square over 2m d square sine over dx square is equal to E sine. The V of x will become 0, and this is E sine. And now, as I did earlier, I will do those steps here. That d square sine over dx square will become minus small k. This is different from this k. It's a big K, and here it's small k. So I will write like this. Let me write it a little different than that one. Minus k and squared sine. Now what this k is equal, as usual, this k is equal to 2me square root over h bar. And this k is positive. Minus we have taken out. Now we will have to solve this equation, and we have already solved this equation in many topics inside or this course. So the solution of this is sine of x in form of sine and cosine. I will write sine kx plus b cos kx. The second order differential equation solution, and we have done it in the infinite square well as well. And now I will utilize this is for x between 0 and a, and now I will utilize the Bloch cell for I will now utilize the Bloch's theorem for this cell, means I will apply it here, and psi of x will become e to the power minus ika, because I'm going this way, and it is a sine k x plus a in plus b cos k and x plus a, and this is in the interval when x is less than 0 and greater than minus a. So this one is, we will have to see here that here this is K, this is capital K, this is capital K, not the small k. This one is capital K. Here we are having the small k. Now I can use another letter, but the book is using this thing, so I am just following the book notations. And now it x equal to 0, x equal to 0 means when I'm exactly at x equal to 0 means the boundary here, then I know that sine must be continuous. Means there will be no breaking in sine. Because you know, when we solve a differential equation, we put boundary conditions on the differential equation. The first boundary condition is that the function will be continuous along the boundary. And the second boundary condition is the first derivative of the function will be continuous. Now here our function is sine, so sine must be continuous at x equal to 0. When it goes from this cell to this cell, the sine is supposed to be continuous, and I can write that at x equal to 0, this equation and this equation should be equal. So this is, let me write, this one is equation 1 and this one is equation 2. When this is continuous, it means equation 1 should be equal to equation 2 at x equal to 0. When I will put x equal to 0, both equations are supposed to be the same. Now look here, when I put x equal to 0 here, then this one will become 0. And this one will become 0 and cos 0 is 1, so, and this equation b will remain. And I will write that b is equal. When I put here x equal to 0, then this is x plus a, so this will be a sine ka in b cos ka. So b equals a sine and capital K plus b cos capital K A. So with this, and it will have this in the multiplication, so multiplied by e minus I capital K A. And let's say this is for equation 3. So I just copied equation 3 here, and now you remember from your calculations which we did for the delta potential value we calculated in equation 2.125. This we did in the second chapter, and over there in the delta function potential, we derived that delta d sine over dx is equal to 2m alpha over h bar square sine of 0. And this let me call equation 4. In that equation, we were having minus sign here, and I have just replaced that sign with a plus because our delta potential here is up. So now I will just start with the boundary conditions that delta, because the first boundary condition was that the wave function was continuous, and now the derivative of the wave function should be continuous across the boundary as well. Delta d sine over dx, and this is equal, if I take slightly close to the boundary, curly psi by curly x, and this is slightly means epsilon on one side minus curly psi over curly x and epsilon on the other side. So it will be very, very close to the boundary because our boundary is having a delta function and it's a very sharp spine. So if I go slightly means epsilon this way and this way, then I'm finding a change in d psi over dx, and now what it will be, I will just calculate the two values at the plus and minus, and d sine over dx at plus means the plus epsilon, and this will be equal to d over dx of the, when I'm slightly on the plus side, then I will have to take the first wave function, and when I'm on this side, then I will take the second wave function. So the first wave function, you remember, it was a sine small kx plus b cos small kx. This was that wave function, and I will calculate this at x equals 0, and when I do calculate this at x equal to 0, then take the derivative first, and this is k times a, and then sine will become cos. So it will be, when apply a derivative, I apply, and then I will apply the limit. A cos and small kx, and that k, small k will come here, plus, or take this one, plus k, small k, b cos small kx at x equals 0. And this will become sine because it's derivative, and this will become minus. So here I'm having at x equal to 0, this will go to 0 and this will go to 1. And I have this thing equal to small k and a. Now I calculate on this side, means the minus side, and I calculate this value. So d sine over dx 8 minus epsilon, this will be equal. Now for the minus sign, I will write the other side, means the other side wave function, and that is d over dx and e to the power minus I, this is capital K A, and A sine, this one is small k x plus A plus B cos small k x plus A, and this I will have to evaluate at x equal to 0.